No.
Archiving started.
Sweet, archiving has started. Good to know.
Okay, so this is
Okay, so we're not going to blow this up anymore?
No, unfortunately.
Okay, that's fine. The only reason I ask is because there's some really nice pictures in here that I like to show. But so welcome, thank you for coming. It's good to see so many faces interested in astronomy, or more importantly, so many faces interested in extra credit. You don't know how many times I've said that at the beginning of one of these talks. So, I'm Jay Dunn. I think everybody here knows me. For the people online, I'm Jay Dunn. I'm new tenure track here at Georgia Perimeter. I was at Augusta State for the year before that. The 3 years, give or take a half a year, I was at Virginia Tech before that doing research where some of this that I'm going to be presenting today was done, and then I've followed up over the past year and a half on some of my own leads that I wanted to explore, which has also included some undergraduate students. So, hopefully those out there watching, and I've already mentioned it to most of the people in this room, eventually I'd love to include some Georgia Perimeter students into getting the feel for what undergraduate research is. I list here some of my main collaborators. You'll see Virginia Tech, Georgia State, where I got my PhD, Michael Crenshaw. I still work in tandem with both of them, moderately. Not quite as much now that the teaching is settled in, but over the summers, I intend to continue that. So, first off, since I know I'm talking to physics students and general public, I feel an introduction is in order for astronomy. What I'm showing you here are three of the major things that make up astronomy and what we talk about. Planets, anybody know that one? I hope everybody knows that one. Saturn rings are kind of a dead giveaway. Then we have two right next to each other. The bottom one is what? Which star is that? That would be the sun. And the picture in the background is actually just another star. So it's just like taking the sun and putting it at some huge distance. One of the biggest problems we run into in astronomy is size scales. It's just something the mind can't wrap itself around. It's incredible, the difference in size between, say, Saturn even and the sun. Next, please. So I need to give you kind of a preface for the kind of sizes I'm going to be discussing. So we have our solar system, we have the Earth. Earth's a big place, right? Everybody's familiar with how big it is, going from one city to the next, even making the trip over from Dunwoody to here. That was a long way. But the Earth, it pales in comparison to the circumference of the Earth, or even more so the distance of the Moon. Then you scale up even bigger, the distance to the Sun, the size of our solar system, which is roughly 1/200,000 times smaller than the distance to the nearest star. 2,000 times smaller than the distance to the nearest star. Give or take a little bit. This is our galaxy, or what we think the galaxy looks like. Clearly, I can't go out and take a picture of it. We're sitting inside it. Kind of hard to do that. But we believe it is a barred spiral galaxy, the bar being this general shape cutting right through the middle there, and we call this the bulge, and these the spiral arms. And I've highlighted the point where our sun is. Yes, we are not at the center of the universe. We're not even at the center of our own galaxy, nor are we even close. We're about half the way out to the edge of our own galaxy. So this distance from here to here is on the order of about 8 parsecs, 1 parsec being roughly 3 light years. It's a very, very long distance. The edge of our galaxy is somewhere around 15 to 20 parsecs, depending on where you want to put your cutoff. So keep this in mind as we get into the talk, because I'm going to be talking about where the stuff I study is relative to this galactic picture, and I'll stick some reminders in there. Oh, I don't have animations. So this is supposed to be a picture of a beautiful barred spiral galaxy, NGC 1300. It's a better picture of what I showed before. Is there any way to get animations on it? No?
Oh, no.
Okay, go back to the previous picture then. I can use that one to illustrate the point. Basically, the majority of what I've been studying, namely quasars and active galactic nuclei, it's nucleus because it's at the center of this guy. So it's down here at the very center and takes up about 2 or 3 pixels in this picture. It's extremely small compared to the big galaxy around it. But it's that important to the galaxy that it's there. Okay, go ahead. And skip to the fifth one, please. So down in the center of every major galaxy, NGC 1300, the Milky Way included, is, I've seen in all of the TV shows, the lurking monster down at the middle. It's a supermassive black hole. Now, up until about 20 years ago in scientific publications, you weren't allowed to say for certain black holes. It was always things that might be something like the theoretically postulated black holes. Now, this is a movie. This is a picture of what is going on down at the center of our galaxy, seen in infrared light. If we can do the movie real quick.
Okay, yeah, let me see if I can share the desktop.
Okay.
I don't know what people might be seeing or not. Sharing.
And Edward, I can see your, are we able to communicate okay? Isn't technology great? It's so useful until it doesn't work.
Well, we got people who are operating it, I'm not sure.
Oh, yeah. That I understand too.
Okay, so now, hopefully, the audience will see what's
On the desktop, sure.
So I'm going to minimize it, and I'm going to have it remove it here.
Okay, so fire that puppy up. And you're going to see the stars, if we can blow it up as big as we can, you're going to see the stars moving around. They're all, everybody can see that, and it's resetting. It's starting from 1994 through 2003, roughly. Then we're going to zoom in, and you're going to see this star carving out a yellow path, that one carving out a yellow path, and those little hash marks are data points, our physical measurements of what's going on. And you'll see that they loop around and make an elliptical orbit, just like Kepler's laws in astronomy, around the very center of our galaxy. So the little cross in the middle, that's the center of our galaxy. You can see everything zipping around that point. You make a nice, pretty ellipse. If I have an ellipse in astronomy, then I have the distance of that object, we call it the semi-major axis. I have the time it takes for it to go around, the period, and we can clearly measure both of those. Kepler's second or third law, we can use that to figure out the mass of what it's orbiting. And that mass turns out to be 10 to the 6th solar masses. That is 1 million of our sun stuck into the center of the galaxy. And you can all see right at the crosshair where that million solar masses is, right? I mean, look at that big bright object down here in the very middle that I'm pointing at now. Everybody sees that? If I take a million suns and put it down in a very confined area, it'd be really bright, right? Did anybody see a bright spot? Because I'm being facetious here. There's nothing there. I'm orbiting 10 to the 6 solar masses of nothing. The only thing we can use to justify that kind of mass in that kind of confined space that gives no light is a black hole. There's no other way to make it. Even if you make it normal material, according to all our laws, it's going to deconvolve and make a black hole. It's all going to coagulate. Okay, thank you. We can go back to the regular talk. So hopefully I've convinced you that black holes are real. Most people don't know that. They think it's just something that we've kind of invented out of math. But that's a case right there of we're looking into the heart of a black hole. Okay, so slide 6, please. So moving right along, we're not the only ones. So what you're looking at here is a deep field image taken by the Hubble Space Telescope. And you can see tons and tons and tons of light points. Okay, and I've mentioned stars before. How many stars are in this field? That would be a goose egg. Well, there's actually billions upon billions in that field. What you're seeing are galaxies. Each one of these little fuzzy dots, you can see this one has a spiral to it. This one's got an arc That's an important proof of general relativity, but that's not for me to talk about. We have lots of little fuzzy blobs here. Anytime it's fuzzy, we know that's a galaxy. And every one of those has a supermassive black hole. Next slide. So I'm going to be talking about a very specific kind of galaxy. And see, again, this was supposed to be a sequence of pictures. I was going to start with a picture of a galaxy, and we were going to zoom into the very core. Because remember, I said that black hole is at the very center and takes up less than a pixel of that center picture. Then you zoom in, and you'll see there's, a big bright bulge. And if it's active, not just a black hole sitting there doing nothing, but gas has been stirred up somehow and disrupted so that it falls down towards the black hole, you'll see an accretion disk that looks something like what you're seeing here. And at the very inner parts of it, physics tells us that it's going to get very hot, so hot that it's going to start to emit light that outshines the rest of the 200 billion stars in that galaxy. These are immensely bright. So anytime you see a galaxy, you'll see that bright hub in the middle. I mentioned that earlier. And at the very center, you'll see these big diffraction spikes because there's a very, very bright thing down in the middle. And we know that's active. And that's about 10% of all galaxies. So that's an artist's conception. This is another artist's conception. We can't actually see the accretion disk with our telescopes. It's too small and too far away simultaneously for us to resolve it, for us to make out what it looks like. So we have to draw what we think it looks like. So you're looking here. Here is my supermassive black hole, and here's my accretion disk of gas that's been funneled down and is now feeding into the black hole. So active galaxies, or quasars, are simply galaxies where the supermassive black hole at the center is eating. Okay? Ours is starving in the Milky Way. It has no food. It has no accretion disk. Now, coming off of this disk, as it gets very bright, another thing physics tells us is that light is going to push on the incoming gas. And as it pushes on the incoming gas, it accelerates it away from that center part. And it's that wind, that stuff that's coming off of the accretion disk. Notice it hasn't gotten to the black hole yet, so it's not coming out of the black hole. It's coming from the vicinity of the black hole. And it's coming out at relatively high speeds. Next, please. So what do I mean by space weather? I say it like that for a reason. We have a bit of a delay on our slides. So Ollie Williams up there, when we ask him what we're looking at, space weather. So clearly I'm not going to be doing predictions of whether we're going to get rain or not. That's a bit different. And there is a division of astronomy that deals with solar system space weather. Again, that's not what I'm talking about. That more regards to our sun and what kind of particles and how many particles are coming out from our sun at a given time, and what we think the sun will do over small time periods. The next one, please. So my kind of space weather is like this guy. Again, this is not in any of the objects I've studied. This is what we think these winds coming off of the accretion disk system, this is what we think they look like when they get out to large distances. So they're moving very fast, they're carrying a lot of material, and we think they become very filamentary like this. This is a real image. This is actually taken from a supernova, an exploding star. So this is what's left over after the star exploded, and we think our thing is very similar to what we can actually resolve in supernovae. Next, please. So, quasar winds, again, it's this stuff coming off at very large speeds, going out to some distance, which we didn't know, and it's going to be pushing on stuff. It's that wind that's coming by us that I'm concerned about. That's my space weather. Next, please. So what do they look like from afar? So these are some of the pictures of known active galaxies. Most of them get names like NGC 4151, NGC 1068. NGC just means New Galactic Catalog. Basically, we got tired of giving them names, said, here's our catalog, here's your number, thank you, drive through it. Most of the time, they're not very impressive because they're very far away. So you get these small fuzzy blobs that have both negative and positive images. And you can, most of the time, make out the fact that these are spiral galaxies that turn out to be active. Next, please. So, if I go and I take a spectrum of one of these galaxies, so what is a spectrum? That means I'm taking a prism or a grating or something that divides up the light so that I'm spreading it out and looking at individual brightnesses for each wavelength. So I have flux or intensity or brightness versus wavelength. If I took a spectrum of one of these objects, which I have here, this is kind of what you would see. You would see a nice power law. So as I go to long or shorter wavelengths, and if you're curious as to what you're at the corner of, this is in the visual. Well, it's in our visual. It's in the quasars UV. So quasars are at such large distances that they experience something called cosmological redshift. Meaning I take its spectrum and I shift it to longer wavelengths. It's a weird thing. It's discovered by Hubble. That's where we get the Hubble Space Telescope's name. And it's something we've known about for a very long time. So this was actually emitted, say, around 2,000 angstroms, or the ultraviolet, and this was shifted into the visual where I can take my telescope, look at it, and take my spectrum. So we're actually at the corner of X-ray, which is down here. Visual would be right out here, which stops right around 4,000 angstroms. X-rays go down to, a few angstroms or tenths of an angstrom. So we have this power law shape. So as I go towards lower wavelengths, my amount of flux or amount of brightness increases. And the other features I have here are these guys. And these are emission lines. And they pop up, they'll have more brightness at those very specific places because it depends on the kind of gas that's making the light. So we have carbon, we have aluminum, we have magnesium. Those are generating those emission lines. Those are called emission lines. That's a healthy spectrum. And I use those spectra to figure out what's going on here. And this is a combo. So this is another deep image. You can see a nice, pretty spiral galaxy right there. And there's another one. This is called an elliptical galaxy, and it is active. We, however, have superimposed these big arches on there because we believe that these outflowing winds go both directions away from the disk, that it's a symmetric issue. So these winds are sweeping out through the galaxy and do all kinds of things on their way out of the galaxy, and all kinds of things once they get out of the galaxy. So I've taken this from back at Virginia Tech, and I've continued working on this stuff, and so now Georgia Perimeter can say we're working on AGN. Okay, next please. Now, my guys don't have so healthy of a AGN spectrum, so we need a doctor. Here in the red, instead of going up towards the blue like every other AGN out there, every so often you'll see one that tanks as it goes to shorter wavelengths. Not only does it tank, it has other features in it that most don't. You can still see this magnesium emission line right there. But right next to it is this huge gaping hole. Tons of light has been removed from my line of sight at these wavelengths. And these are also due to certain elements in my line of sight. It's because of these are blue shifted with respect to rest frames. So Doppler tells us that those are outflowing. They're moving away from this background source, moving towards us. So it will look bluer than it really is. So these are how I know there are outflows, even though I can't see them. And the big question for a long time was how much mass, how far out, what are they? We know they're moving at speeds of tens of thousands of kilometers per second. And to put that into perspective, The Earth's velocity around the sun is only 30 kilometers per second. So these things are trucking, hauling backside. Next, please. So here's a case of one that we found in a survey. And most of the time when I talk about AGN or quasars, I'm going to put SDSS, J, and then a big phone number. You do not need to know the phone numbers. It's simply the sky positions for that particular object because each one's going to be unique. So that's how we tend to do it. SDSS is the Sloan Digital Sky Survey. I'll mention them again here in a second. But you can see, as this is a very, very far away quasar, so that means I'm shifting a lot into the visual. When you do that, you've got a place here at rest wavelength of 1200 and shortward of there. That's a mess, isn't it? Would you like to measure stuff in that? I don't. I have to, but I don't like it. That's called the Lyman alpha forest. It's only important because it messes stuff up for me. I like to have nice, pretty lines that I can simply measure. That makes my life miserable. And we have to search through that kind of stuff to find some of the things we're after. And you can see that this guy has one of those big absorption lines. We call those BALs. B-A-L, broad absorption line. We have emission lines. We have absorption lines. Okay, moving right along. This was the bane of my existence for about a year and a half. This is my personal favorite, SDSS-J, 0318-600. Now, some BAL, most BALs, have only carbon signatures. So you'll see a very specific line that if they're going to have any absorption, it's going to be from carbon. There are rare cases, very rare cases, where I will have them showing lines from iron, and we will call them iron lowballs. Okay? Don't need to know too much about it, except these special cases are the ones that allow us to actually figure out how far away they are from the center. So this gets us one of our unknowns. So let's go to the next slide first. I'll come back to that. So why should you care? Again, I'd like to have animation, but sorry. So the text is all covered up, but there are current problems, one of which is here in the forefront. This is called the Millennium Simulation. Okay, so some really, really smart guys, Carlos Franck, I think, is one of them, and they basically put physics as we know it in a computer box and said, go. Let's start the Big Bang and just let everything go and see what kind of universe pops out. And this is the universe that popped out. And it looks very similar to ours in most regards. It has a very filamentary structure. Like if we look at all where our galaxies are and the gas and everything, it's very filamentary, very foamy looking, kind of like this. If you imagine this as 3D, it'd be kind of foamy, right? The problem is that the galaxies at the middle, they're black holes. There's a very specific relationship as to how big a black hole is compared to how big its host galaxy is. Right? Because it's centered down in the middle. It's nested at the core. And that relationship is very, very specific. And they, when they ran this, did not get that relationship out. The black holes were far too massive. They were eating too much. So they needed a way to control the black hole diet. And that's where we come in. There are other areas where winds can come in. So the winds are basically removing mass from the black hole, preventing it from getting down and getting eaten, right? I eject that out at very high velocities. It leaves the galaxy entirely. It's moving so fast. Nope, not yet. Other things that winds do, this is why you should care. These winds, as they're going out, they carry a ton of energy and a ton of momentum. So let's say we have a star-forming region in a galaxy. We're building new stars, baby stars. Let's say our sun was being built, and one of these winds came through. It would sweep up the gas that would be making our sun and our planet, and it takes it all away and carries it out of the galaxy. This is one way you can shut down star formation. Meaning, these are important because if one came through when we were being born, we wouldn't be here. If the Milky Way decided to burp past us, that would be bad. And in order to do all of these things, we talk about bolometric luminosity, or how bright the object is in general. No need to know bolometric. Just know luminosity, how bright it is. We need 5% of that energy put out in mechanical energy in the form of the wind to get all of this to fix. So the question is that how much we're getting? And nobody knew. We had no way of getting it until about 3 or 4 years ago. So what do we think we know about them? Well, we know roughly the frequency. All I have to do is take a spectrum of a quasar, and I can see whether it's got that line, right? So I know how frequently we get these outflows. Velocities, I can tell you expressly from the spectrum, right out of Doppler shift, how fast they're moving. It's the easiest calculation in the world. Undergraduates can do it. As I take my little jab at my 2211 students. Is that me? Feedback? Okay. No big deal. Now, to get mechanical output, how much mechanical work and energy is coming out of these, we need two unknowns. We need the distance, and we need the fraction beyond this information, beyond the velocity. We need the velocity, because, right, 1/2 mv squared. I need to know the mass. In order to get the mass, I need to know how much material. So if I shrink it down to a little arc, a cloud being ejected, I need to know how far away it is and how big it is. Now, step one, go ahead, sorry. Step one, we could fix for those very specific objects that have iron absorption lines in them. So these rare guys, we're able to look at the lines, do some complex analysis, I'm not going to get into all that mess, and say, okay, it has a number density, a number of particles per cubic centimeter of whatever. Turns out to be something like 10 to the 4 particles per cubic centimeter. Now, a good vacuum here on Earth is on the order of like 10 to the 9, 10 to the 10. So it's actually better than what we call a vacuum. But compared to interstellar space, which is about 1 particle per cubic centimeter, it's actually quite a bit of material. Let's see. Yes. So the question is that density can be used to get distance. Again, complicated, not going to get into it. But the bottom line, let's go to the next one, it gets out to several kiloparsecs, several thousand parsecs. So here we are. Here's where the black hole is in the accretion disk. And this outflow is out, at least in 0318, the object I showed a minute ago, at 6 kiloparsecs. There's also a bit of a debate whether it's 6 or 20, because there's a variable that we couldn't account for. And that's kind of the focus of my research now. But we assumed that it was the smaller of the two, because we wanted to know if that was enough to get us the energy we need. And we had a handful of these guys. And it turned out that those energies were on the order of 1 to 2%, and they were asking for 5. Now, in astronomy, a factor of 3 to 4, that's okay. Physics, you know, they like being much more precise than astronomers. Astronomers, if we can get within, you know, the ballpark, we're okay. So people are going back now, actually. They saw my paper and another colleague of mine's paper. He was actually an undergraduate. Saw our papers and said, okay, we need to tone down that 5%, we think, because we can get a good amount of energy from these winds now that we know something about how much energy they have. So that's the first uncertainty. Now let's talk about the second biggest uncertainty. The second biggest is the size of it, right? And the way we do that, I mentioned we have frequencies. So what you do is you look at several different sight lines to quasars. And this is supposed to be animated, but that's okay. It's okay, it's fine. So you look at several different sight lines. And you assume that sample you took is representative of the whole. And each one of those sight lines, there's one behind this too, each one of those sight lines, those little circles, you count them up and you compare it to the whole. And that's just like saying if I integrate all of those sight lines, those small areas of the total sky, I can figure out how much of the sky is covered from the background source. It's an approximation, but it should be fairly decent. And so you take all of these and you integrate them together and you see a wind that's about 20% of the total sky from the point of view of the quasar. Now, that's only for those carbon guys. For the iron guys, we see them extremely rarely, right? I mentioned that before. Like 0.3% of the time as opposed to 20% of the time. That's 2 orders of magnitude difference between the two. That's a lot, even in astronomical standards, to try and just wave off. Okay, next please. So how do we fix it? Because we don't believe that it's actually that those are any more or any less covering or any less size. They're just less frequently seen. So what we did is we wanted to look for guys that we could do our analysis on, like with the iron, but with something that was similar to carbon. And so we went looking for sulfur. And that's why I showed you this guy. That is the line alpha forest. We had to go digging through there looking for sulfur lines. It's not fun. These 2 wonderful ladies worked with me at Virginia Tech, Courtney and Ashley, and bless them, they were actually able to pull out some objects. As soon as we're ready. No, it's fine, it's fine. We found 4 objects. It's 3 now. We're still putting this paper through a referee, and we had to axe one of them because we got better data. But still 3 out of like 100 to 150. So that's 3% as opposed to 0.3%. And from what we can tell, these guys are going to give us roughly the same energies, roughly the same distances. So we've answered the problem. We're still seeing that they're at large distances, enough energy to do what we think they're going to do, and representative of all of these Bal quasars. Okay, next please. Now I have to go back to a little bit of introduction before I go on to what I'm doing currently. These are projects that we're wrapping up. We did the first one my second year of my postdoc, and the other one I just, like I said, I'm going through the referee process now. So there's no more work really to be done on that, except we've got better data now. We can actually start measuring some stuff. This is known as the unified model for AGN. So when you go looking at the core, you'll have, this is a cutaway, and this is kind of an artist's conception. I like artist's conception better than this, but this gets the point across. We have the black hole down in the middle. We have an accretion disk, the gas that's being fed, right? Then we have a ton of material spiraling around down in there and some other material out here. Then we have this thing called the obscuring torus. So if we go to the next one, we can see clearly in the spectra of Seyfert galaxies, which is just a type of AGN, it's a type of quasar, just a lot closer to us. Makes life easier. You see this classic spectrum where I said it was going to increase as we go to shorter wavelengths. And we see our emission lines on top of it, right? Now, these emission lines are nice and broad, so we call them broad emission lines, just like broad absorption lines. Yes, we're very, very creative when we name our stuff. On top of each of them, we have a narrow line. That's for NGC 4151. If we look at NGC 1068, look at this line compared to that one. This one is significantly narrower than the base part of it, but it's about the same width as the top part. So we know we have a dichotomy here of 2 different types of objects. We have ones that show both narrow and broad lines, and ones that just show narrow. These are oxygen lines that both of them have. They're overlapping on top of one another. So how do you explain with one AGN model 2 totally different spectra? And if we go to the next slide, so we go back to the, as I like to refer to it, the exploding bagel, because it looks like a bagel that's exploding. Got its name from a Georgia State professor. So if I'm looking in this way at the black hole, then I'm not going to see a lot of this gas that's moving around really fast down here that Doppler shifts the lines so they get broad. This stuff out here is not moving very fast, so it would create very narrow lines. So we have a broad line region and a narrow line region. And if I'm looking along the axis of this obscuring torus, something that's blocking the stuff down here, all I'll see is the narrow line. But if I'm looking through the whole of the donut, I'll see the narrow lines, I'll see the broad lines, I'll see the accretion disk, and I make my typical spectrum. So it's simply a point of view. Now, why am I telling you about this? Don't change yet, because I have to explain something first. So, like I said with 0318, there are two distances that we kind of calculated. One was at 6, one was 3 to 4 times further away at almost 20 kiloparsecs. That's a huge uncertainty. That's a factor of, 3 to 4. How do we fix it? Well, the question is how do we generate these very special cases? And we, again, turn to sightline. What we think is happening is I have a normal outflow, so it's getting kicked out from the center and shot off into the galaxy. If I'm looking right along this edge, I'm going to kind of graze the torus. And I'm going to filter out a ton of this light coming from this stuff down here. And that's crucial for making these special kind of lines, toning down the brightness that the outflow sees. Because if I go to full brightness, I'm going to change it to that regular carbon kind. If I go down here, then I'm not going to see anything at all. I don't have my flashlight on in the background. No flashlight, I can't see the material in the way. So we want this very special case where we're grazing the side of the torus. And that's the only way we can think of. There are two ways. It could be that they're just genuinely smaller and rarer, but it could also be that it's the normal kind of outflow with this crazy, wild happenstance of a sight line. I can fix that problem. I can tell whether it's one or the other. Go to the next, please. So I can tell when I'm looking at these outflows if I'm here or here, because that's a 300 to 400% increase if it's out here of the mechanical energy. That's huge. It would be too much, more than likely, and it will. There are some cases where you could actually rip entire chunks of the galaxy out. And that's clearly not happening. So we want to say it's down here. So I'm obscuring, I'm getting that really odd sight line. Okay, next one, please. So what I want to know is, do I have something in my way here that's blocking the light getting out to my outflowing wind? And the way you can do that is with those lines I was showing you a second ago. So if we remember the unhealthy spectrum, remember how it dropped off as we went to the blue? That can be caused by this, by something in the way. But what we don't know is if, and almost all of these special cases, all of these FE lobals, have something that's causing it to get that abnormal spectrum. But is it before the outflow, or after the outflow, or with the outflow? It could actually be mixed in. It's dust. So is the dust before it, with it, outside of it? If it's outside of it, that's the extreme case where it's at 20 kiloparsecs. If it's interior to it, then it's at the inside case. So what I can do is I can look and I can measure the reddening, or the amount of unhealthiness we have in our spectrum. Then I can also look at the lines. Remember I had the two different lines. Can we go back to the unified model? I have the two different lines, the narrow lines and the broad lines. Now, the torus is in between these two, right? So if I have this grazing sight line, then I should see the spectrum unhealthy. I should see these lines created by the broad line region as unhealthy too. And the narrow lines would be perfectly normal. But if it's exterior to all of it, then it's all going to be unhealthy. I can differentiate whether that's the case. And from what I can tell so far, it looks like I'm going to have the unhealthy spectrum with the unhealthy broad line region and perfectly normal narrow lines. If the narrow lines have the unhealthiness, then I know it's exterior at least to this. That doesn't mean it's outside of the quasar or outside of the wind, but it means that it's not necessarily interior to it. If I can put it between this and this, I know for a fact it's interior to the outflow. I don't remember what we were on. So 32, I think. Oh no, ongoing project. Yep. So I sent Jamie Pate at Augusta State, she was an undergrad, looking for objects that had two requirements. They had to have the outflows, they had to have those broad absorption lines, and they had to have the narrow lines. Most of the unhealthy ones, you can't see the narrow lines at all. Nothing. You don't see much in the way of broad lines either, because it's all been eaten away by those big absorption troughs. So since I don't have those in most cases, I need to find those rare exceptions where I have the lines and I can measure them. So I sent her looking. She found a whopping 3 out of 10,000. She dug through a whole lot of spectra. This is the SDSS, Sloan Digital Sky Survey. They've surveyed a huge chunk of the sky, looking at, they have over 100,000 quasar spectra, and they have over 1 million quasars measured what's called photometrically, basically just counting photons from the guys. So she went through about 10,000 spectra and found 3. One of which turned out to have really high resolution data that I had through another resource. So that's the one I'm working on currently. Next slide, please. These are those 3 objects. And that top one, you'll notice that this gets truncated in both of these cases, and they're slightly shifted, okay? Because they're at slightly different distances, so it shifts it into the visual a little bit differently. So the top one is my really nice spectrum that I got from the Magellan telescope out at NOAO in Arizona. So that's a very, very large telescope, 4 meters, I believe, and very high resolution, meaning very finely chopped up, so I can get more detail. And you can clearly see I have nice, strong, narrow lines in these guys. And those are the crucial pieces I need to figure out whether the reddening, which is, you can see this one's tapering off, that one does too. This one actually is fairly normal spectrum. So I have to justify that, but I have some ideas. So I've measured the reddening for the top one, and I'm currently in the process of measuring the line strengths for the top one. Okay, 32, please. So hopefully I will have an answer very soon. And I'm looking for people, for those of you who are online, you guys have already made my advertisement too. I'm looking to know what kind of interest there is here at Georgia Perimeter. So please, if you're interested in research, not just about astronomy, biology, chemistry, I want to get this atmosphere built. Because even though it's a 2-year school, it's great if you walk into a 4-year school after you get your AA and say, I've done undergraduate research. I know what I'm getting into. That's very, very impressive to people who are looking to take on undergraduate researchers or maybe graduate later on down the road. So thank you very much for your attention, and I'll take questions now.
The email address is j.dunn.
At GPC. You can do j.dunn or my initial J, then last name. So yeah, I'm good for questions. Fire away.
You know how there's a hydrostatic equilibrium in the sun between light pressure and gravity? Yep. So why does light pressure for a black hole win?
So, just in case they didn't hear online, the question is in the sun we experience hydrostatic equilibrium, meaning gas is being compressed down by gravity, and light is supporting it. That's why the sun doesn't just collapse. So the light is, well, partially light pressure, but also gas pressure. Gas does it too. So there's a lot of, it's thermodynamic equilibrium, actually. Local thermodynamic equilibrium. So in the case of the stuff falling in towards the black hole and getting pushed out, I don't have any extra stuff piling on top of it. So all I have is gravitational force. So as long as the light force, or force from light, the light pressure, I guess is a better term, is larger than that incoming force from gravity, I'm going to push it out. Imbalance of forces, Newton's second law, right? I'm going to accelerate it outward as long as that photon pressure is larger than the amount coming down. And there's nothing piling on top of it to increase the pressure, pushing down on it.
Okay, just actually a couple of questions.
Mm-hmm.
The first question, do you know anything about comet Lennon, and could there possibly be a high gravity object following it?
I don't know anything about Comet Lennon, sorry.
And another question here, what kind of short-term goals should I make to seek a career in research that would be advantageous?
Short-term goals. So my first thought in that arena is find a mentor. Find somebody who has done research. Even if they're not doing it right now, find a mentor, somebody who can kind of coach you, because they're going to be able to tell you what you're looking forward to down the road. That's really the key. If you can get into undergraduate research, if you can, even if it's just a lot of people when I was at ASU would do projects that weren't publishable, but they were like designing a new lab. And so if you can get in even one foot in the door to doing some research, that's a great way, because not only are you building your CV or resume, you're also learning about what it is you're getting involved in. I know one person in particular, she's a very successful postdoc right now at University of Maryland, and she's gotten the impression of what research was before, and now that she's actually gone out in the field, has realized she hates it. She hates the politics of it, and so she wants out, completely out of science. So it's good to get that as early as possible to help you make up your mind as to what you're wanting to work on. So that's my advice. Find a mentor, get advice from a mentor, somebody who's been there, done that.
These things are so far away. Like, how do you know that there's not other objects in the sky that block your view?
Well, one, if it blocked your view, you wouldn't see it. Mostly what we do, so we've got the Milky Way around us, right? There's a region of the sky that cuts through the Milky Way. Basically, we don't see anything quasar in that direction. We look out of the plane of the galaxy, which is relatively thin. So as long as we don't have a ton of gas, which, sometimes you do and sometimes you don't, we have the actual sight lines mapped out, so we know how much gas there is in each direction, roughly. And we can actually see tons of quasars out above and tons below, and those are the ones we're looking at. So, and sometimes you'll see pictures of quasars, like I showed some of the deep field images. And you'll occasionally see an object with diffraction spikes. That's a star. So you know it's there. And luckily for us, the universe is sufficiently spaced out, or at least our galaxy is, that you don't get a lot of superimposed stars on the important parts of the quasars.
So we're literally only looking in two directions.
Well, kind of. I mean, you're looking out at, roughly 130 in one direction, 130 in the other direction, and missing, kind of a quarter of the sky. Andre. Oh, sorry. Sure. Sure.
Okay, two questions quickly. The first one, it says that light has a phase of a black hole. If light is massless, what pulls light into the black hole center?
So this is a relativity question, actually, and hopefully you kids in my 2212 class will get to talk about it a little bit. But gravity, once Einstein came along, general relativity, we can describe gravity rather than a long-range force that physically, ties a rope to you and pulls you. It actually bends space-time. There's a great demo I love to do for this. You take a big sheet, like literally a bed sheet, and you get all your students to hold it around and you pull it taut. And then you sit something heavy in the middle, and it bends that sheet. So if I were to roll something across it without that in the middle, it would go in a straight line. But once I put that in the middle, it bends the sheet down. I try and shoot it across, it's going to bend and have its path curved by the object in the middle. And that's exactly what's happening with a black hole. I'm bending space-time so that my straight path is no longer straight from my point of view. From the point of view of light, it's still a straight line. But from the outside point of view, it's been bent so it gets curved and actually wraps down into a spiral, that kind of thing. So what was the second question?
The second question was that I was confused with winds and from where they are coming. These winds can't come from the black hole itself.
Right. I tried to be specific when I said that. The winds aren't coming from the black hole. I have gas that's coming down and feeding the black hole. And before it gets to the black hole, it creates an accretion disk. So here's the black hole. The accretion disk is from here to here. It encompasses a disk out around it. And the winds that I'm talking about are being ejected off of that disk before they ever make it to the event horizon. And Andre had a question. Well, we have some picture of stellar remnants. Sun won't blow up. Don't worry. Sun will kind of give out and puff away and die, very weakly. It's a moderate star. Anything over 8 solar masses, so our sun is obviously 1 solar mass. Anything over 8, it will expand and burn all kinds of things other than hydrogen in its core. It'll get to iron. You can't fuse iron. So it will just stop and start to contract. And as it starts to contract, it'll get to a point where a certain kind of pressure called neutron degeneracy won't let it get any smaller. And all that material that was being supported starts falling in, thanks to gravity. And when it gets down to that core, which can't go any smaller, it's like hitting a brick wall. All that stuff hits that and gets shot back out. A shock wave rips through the outer part of the star and just blows it apart and leaves that core left over, and all of that gas gets ejected at thousands of kilometers per second. And that was what I was showing you a picture of, is that gas that had been ejected. Anything else? Maybe one more? Anybody else? Okay. Oh, okay. Hopefully you enjoyed it. Hopefully, like you said, if I got 50% across, I'm happy.
Okay, well, let me stop the archive and then
Okay.
Maybe I'll manage either later today or tomorrow. Definitely I'll send out the link to the archive.
Okay.
And then everybody can go back in, or people have missed it to any part of it.
Sounds great. Thanks, everybody online. Thanks, guys. I appreciate you coming out.